Okay, so sometimes what happens is that the pole of a function lies on the path of the integration. So you decide you want to do a certain type of contour, like a rectangular contour, and you end up with a pole which is on that path. So we're not allowed to integrate through a pole, but what we can do instead is integrate around the pole. So that's really what we mean by poles, simple poles on contours. They're not strictly they're not on the contour. But we deform the contour to give you a semicircular little bit if the pole is on a straight line bit. It could occasionally it can be in a corner, in which case you've just got a quarter circle. Okay, so we need to then modify the residue theorem. So it's modified in the way you would guess that basically if you've got a pole on a contour and it's on a bit giving you a semicircle, so it's on a straight line, the smooth part of the contour, then it's sort of like you're integrating. You count it as a half a residue. So basically, the formula you end up with is 2 pi I times the sum of the enclosed residues, any residues of poles inside, plus, and then half of this for residues on the smooth part of the contour, so looking like this. And if by any chance you end up with a contour, this is fairly unusual, but if you end up, with a contour which has a pole that's a corner, a right angle corner, then because you've got quarter circle, this actually counts as a quarter of the 2 pi I, so you end up with pi by 2 times I times the residue at any right angle corners of the contour. Okay, so I think I won't go through why that is. I've given the explanation here. Really, all you have to do is go back and look at where the residue theorem came from, and the working is pretty much the same. So I'm happy for you to just use this result here without proof. Now the important thing is that okay, well, I suppose I do actually need to just talk about this. So if we just concentrate on what's happening from here to there, from A to B, what we're doing is we're integrating our function phi from A up to just before x0. And then we're integrating around here. And then we're integrating from just after x0 up to B. Okay, so that's these two integrals here. This integral here will end up giving you the I pi times the residue at x0. This bit here is just the rest of the contour. But now we're interested in what's the actual meaning of these two integrals here. And this is actually given a special meaning. When you're integrating something which has a singularity between the limits, so you've got a real integral of phi, and you've got a singularity, phi has a singularity and it's a real integral, so it's somewhere between the limits, then strictly that integral doesn't exist because you're trying to add infinity. I mean, if you think of an integral as working out the area under a curve, you're summing something which is infinity, and you're not really allowed to do that. But what you can do is you consider these two integrals and you just take the limit as r gets smaller and smaller, and that's which is what we've got here. And if that limit exists, then it's called the Cauchy principal value, and it's written in this way. Sometimes people write it as PV, but we're going to write it as A to B, and then a line through the integral which sort of says that there's something funny goes on in the middle of the integral and it's broken. So it's basically broken into 2 bits. You integrate up to the singularity, just before the singularity, and then from just after the singularity, and you make this distance r get smaller and smaller. As long as this limit exists, converges to a finite number, then you're okay, and we can define this Cauchy principal value. So basically what happens is that if you do the contour integral, then you automatically get the Cauchy principal value. This automatically gives you the Cauchy principal value. So let's do an example. So sine x over x. So how can we integrate that? Well, this integral obviously has a removable singularity at x equals 0. So the integral itself doesn't need a line here. It's finite at x equals 0. But if we want to actually evaluate the integral, how can we do it? Well, we're going to use, it's a Jordan's lemma type integral, right? So sine x we can write as the imaginary part of e to the ix. So we're going to have to evaluate e to the ix over x via this type of thing, imaginary part of this. This is when we get problems, because e to the I z over z does have a singularity at z equals 0. So if we do the usual semicircular contour, that is going to have a pole at x equals 0. So we are going to have to integrate, we are going to have to indent the contour at z equals 0. Now in this particular case, there are no singularities inside the contour. So this bit here is going to be 0. We only get I times pi times the residue of this function at z equals 0. So the residue is easy to calculate. You can use the p over q dashed. Q is z, so q dashed is 1, and e to the 0 is 1, so the residue is 1. So we get simply the answer to this integral is I pi. And we want the integral we want is the imaginary part of I pi, which is pi. So sine x, integral of sine x over x is pi. Now this integral strictly doesn't exist. It's cos x over x. It doesn't exist because it's infinite at x equals 0. The integrand is infinite at x equals 0. But the principal value does exist, and we can simply get the principal value by taking instead the real part of this. And the real part of I pi is 0. So the principal value of this integral is in fact 0. Another example. So here we definitely do have a pole on the real axis, because when x equals 1 it goes to infinity. Again, if we don't have this line here, then strictly this integral doesn't exist. So the line means we're going to take the principal value. Once we know we've got this line here, then all the other methods just work as normal. But whenever we have a pole on a contour, we just count it as half a pole. So the integral has a pole at x equals 1, as we said, needs to calculate the residue, and it also has poles at x equals plus or minus I. So we use the usual semicircular contour method, but indent it at z equals 1, where the pole is. So the only enclosed singularity is at z equals I, and it's straightforward to calculate the residue there. Okay, so we end up with 2 pi I times the residue at z equals I plus pi I times the residue at x equals 1, z equals 1. just as a reminder, it's when we start to get a mixture of when we start to get complex numbers appearing in our expressions for evaluating the integral, it's easy to make a mistake and end up with a complex number here. If you do end up with a complex number here, you make a mistake, just remember that you expect to get a real number. So always be very suspicious if you end up with a complex answer. You've made a mistake somewhere, basically, unless obviously if you've got complex numbers here, then okay, you could end up with a complex number answer. But if this is real, the answer has to stay real. Okay, so you can now do 24 and 25. The next section just talks about how to get principal values with Mathematica, and we're done.